Hello everyone, this is another lesson in our digital systems video series. In the previous lesson, we introduced the concept of truth tables and learned how to determine their structure. We learned how many input variables a circuit has, how many columns are needed, how many rows must be created. Now it's time for the next step. In this lesson, we'll focus on two topics: how to fill the input columns of a truth table correctly and the output column. In other words, how do we organize zeros and ones so that every possible input combination appears in the correct order? This is a very important step because if the inputs are filled incorrectly, the entire truth table becomes incorrect. So let's get started. As we saw in the previous lesson, the truth table lists all possible input combinations and later the corresponding output values. For a while, we'll work only with the input side and then how to fill the input column, okay? For this example, we have a logic function with three input variables, a, b, and c. Notice that this Boolean expression corresponds directly to the logic circuit shown here. Each term of the expression represents a specific logic operation inside the circuit, okay? Now, before determining the output values, we first need to generate all possible input combinations. Since we have three input variables, we calculate 2 to the power of 3, which gives us 8. So this truth table will contain 8 rows, that is 8 input combinations. Pay close attention to this part, because the input columns of a truth table cannot be filled randomly. We cannot simply place zeros and ones in any order. There's a rule behind this pattern, and this is exactly what we're going to learn now. So here, I'll not just show you how to fill the input column, I'll also show you why this pattern works. First of all, notice that each input variable also has a different level of significance. For example, the variable a is the most significant bit, or MSB, because it has the highest binary weight, while c is the least significant bit, or LSB, okay? Because it has the lowest binary weight and changes more frequently. And B represents an intermediate bit. Let's start with the column A. Since A is the most significant bit, its values change more slowly, like this. So the first half of the column is filled with zeros, and the second half is filled with ones. In other words, column A has a weight of 2 to the power of 2, which gives us 4. So the values in column A change every 4 rows, okay? That means 4 zeros followed by 4 ones. Now let's analyze the column B. Column B has a weight 2 to the power of 1, which gives us 2. So the values of column B change every 2 rows. That means 2 zeros followed by 2 ones. And finally, let's analyze column C. Column C has a weight of 2 to the power of 0, which is equal to 1. So the values in column C change at every row. That means 0, 1, 0, 1, 0, 1. And notice that this pattern repeats to the end of the column. Notice that as the binary weight decreases, the bits change faster. So this is how we fill the input column of a truth table with 8 rows. Okay, it's very simple. It's very easy. Now let's analyze a more complex example. This time, the logic function contains 4 input variables, a, b, c, and d. Once again, notice that this Boolean expression corresponds directly to the circuit shown here. Each operation in the expression is represented by each logic gate inside the circuit, okay? Since we now have a logic function with 4 input variables, the truth table will contain 16 input combinations, like this, okay? And just like before, each input column has a different binary weight. A is the most significant bit, and D is the least significant bit. And we have these two intermediate bits, B and C, okay? Let's analyze the column A. The column A is the most significant bit. Since A is the most significant bit, it changes more slowly than all other columns. That is, it has a weight 2 to the power of 3, which is equal to 8. So its values change every 8 rows, okay? 8 zeros followed by 8 ones. It's very easy, okay? Now let's move to the column B. It has a weight 2 to the power of 2, which gives us 4. So the values in column B change every 4 rows. That means 4 zeros, 4 ones, 4 zeros, 4 ones, and this pattern follows into the end of the column. Next, we fill the column C. Column C has a weight 2 to the power of 2, which gives us 2. So the values in column C change every 2 rows, like this. 2 zeros, 2 ones, 2 zeros, 2 ones, until the end of the table. And finally, let's analyze column D. Column D has a weight 2 to the power of 0, which is equal to 1. So the values in column D change at every row. That means 0, 1, 0, 1, 0, 1 until the end of the table. And now we have all 16 possible input combinations for this truth table. Notice that these values are not random. We can begin determining the input column. And once the input combinations are complete, we can begin determining the output values of the logic function. Now, let's focus on how to determine the output of a truth table. Actually, there are two different ways to determine the output column. First, we're going to evaluate this Boolean expression step by step, term by term, using input values of each row, okay? And then I will show you a faster way to determine the output column. But it's very important you learn two ways to determine the output column, okay? Before we start combining terms, let's identify the complemented variables in the expression. Here we have A complemented, C complemented, and D complemented. Remember, the complemented variable simply inverts the original variable, like this. If the input is 0, the output will be 1. And if the input is 1, the output will be 0, like this. As you can see, all the column A was inverted, okay? Where it was 0 becomes 1, and where it was 1, it becomes 0. And the same thing happens to the other columns. For example, the column C, 0, 0, 1, 1, 0, 0, 1, 1, and C negated, 1, 1, 0, 0, that is, it was inverted. The same thing happens to the column D. For example, column D, 0, 1, 0, 1, and the column of D negated, 1, 0, 1, 0, 1, 0. It's very simple, okay? So here, we fill each column by inverting the corresponding input values. Now that we have all complemented variables, we can move on to the next step. Notice that this part of the expression is inside the parentheses. Just like mathematics, parentheses define the order of operations. So we evaluate C complemented plus D complemented, which means we'll evaluate the column C negated and D negated, okay? As you can see, this is an OR operation because OR operation performs Boolean addition. And as we learned in the previous lessons, an OR operation, the output will be 1 if at least one input is 1, okay? So we combine the values of C complement and D complement for each row, like this, okay? The output is 1 if at least one input is 1, okay? The output will be 0 only when both inputs are 0. Now we use this result to continue evaluating the expression. Next, we evaluate A and B, okay? This part of the expression. So we combine the column A and B. In AND operation, the output produces 1 only when both inputs are 1, okay? Like this. As you can see, the output is 1 only when both inputs are 1. Pay attention. Now we are evaluating these two columns, A and B. So we compare A and B row by row, like this, okay? The output is 1 only when both inputs are 1. So according to the Boolean expression, we combine both results. We take A and B being multiplied by C negated plus D negated. As you can see, this is another AND operation. So this column represents the condition where both parts of the expression are true. The output is 1 only when both inputs is 1. The output will be 0 if at least one of its inputs is 0. Now we have a single bar covering all this part of the expression. So we must invert all these columns, okay? Where is 0, it becomes 1, and where is 1, it becomes 0, like this. And finally, we combine everything to obtain the output column. We combine this column with A negated. As you can see in the Boolean expression, this is an AND operation. This column represents the final value of the expression for each row, okay? As you can see, the output is 1 only when both inputs are 1. Now, after all intermediate steps, we can simplify the visualization. It's very simple, it's very easy, okay? Notice that we didn't guess the values. We systematically evaluated the expression using rules of Boolean algebra. This method is reliable and always works, but it can be time-consuming. So the question is there a faster way to do this? Yes. And that's what we're going to explore now. Actually, this is not a different method. It's just a faster way to think about the same expression, okay? Now that we understand the step-by-step method, let's explore a faster way to determine the output. Instead of computing every intermediate step, we can analyze the behavior of the expression. Let's start with the first input combination, okay? 0 to the variable a, 0 to the variable b, 0 to the variable c, and 0 to the variable d. We substitute the values directly into the expression. A is 0, so a complemented becomes 1. C is 0, so C complemented becomes 1. And D is 0, so D complemented becomes 1. Now we evaluate the expression step by step, according to the Boolean operations. In this case, we evaluate first what's inside the parentheses. 1 plus 1 equals 1. And then multiplying all these terms, we get 0. And as you can see, this term is complemented, so its value is inverted. And finally, we evaluate 1 times 1, which gives us 1, okay? So the output is 1. So for this input combination, the output is 1. Now let's look at another input combination. Again, we substitute the values and we evaluate the expression, okay? And we reach the output 1, okay? Let's look another. Again, we substitute the values and we evaluate the expression. We reach the output 1, okay? Let's look at one more input combination. Okay, substituting the values and evaluating the expression, we reach the output 1. At this point, something interesting starts to happen because we begin to notice a pattern. In this case, the pattern is very clear. Whenever the variable a is initially equal to 0, the output becomes 1. Okay? It doesn't matter what the values the other variables have. And we already proved this using the first input combinations we evaluated. Notice that we have a variable a in two different places. Inside the brackets, okay? And its complemented form outside brackets, participating in an AND operation. Okay? Now pay close attention to the order of precedence. The expression inside the parentheses is evaluating first. Okay? Because operations inside the parentheses always have higher priority. And remember, everything inside the brackets is complemented. So if a is initially 0, okay, its complemented form becomes 1, okay? Now let's analyze the expression inside the brackets. At some point, the terms inside the brackets will be connected through logical multiplication, which means an AND operation. And as we already learned from Boolean algebra, 0 and anything always results in 0. So the final result inside the brackets becomes 0. But remember, the entire bracketed expression is complemented, which means this 0 becomes 1. So both values are now equal to 1. The final output becomes 1. Okay? In summary, if the variable a is initially 0, the output always will be 1. I know, at first this process may seem complicated. But with practice, we will gradually develop the ability to recognize behavior and patterns of logical functions. So instead of evaluating these rows one by one, we can now fill a larger portion of the output column immediately. Now let's analyze what happens when a is initially equal to 1. In this case, the output tends to become 0. And we can verify this by evaluating the expression using the logical values of row 8. Now that we have identified this second pattern, we can infer that every remaining input combination where a is initially equal to 1 will also produce an output equal to 0. And the reason is very important. We'll always have an AND operation involving 0. And as we learned from rules of Boolean algebra, 0 and anything is always equal to 0. So regardless of the values of the other variables, the result of this part of the expression will always become 0. Therefore, all remaining rows that satisfy this condition will always have an output 0, like this, okay? At this point, we are no longer evaluating the truth table row by row. We are understanding the logical behavior of the function. So in this lesson, we learned two different ways to determine the output column of a truth table. First, We used step-by-step method, evaluating the expression term by term. Then we learned how to identify the logical pattern in the function, allowing us to determine the output column faster. This is extremely important because in digital logic, understanding the behavior of a function is often more powerful than simply memorizing rules. Now it's time to practice this concept. So in the next lesson, we're going to solve several truth table exercises together, just applying the pattern recognition method. And as always, take your time, practice the process, and try to understand the logic behind each operation, because that is how the real understanding is built. Thanks for watching, and I'll see you in the next lesson.